All right, let me start recording. And so I'll try to do a work problem of the day, at least for these next couple days. And we'll be doing more of it on Monday with the project. The first work problem, so you guys have another homework due on Monday. And so let's do a problem from that to help you guys out. It's one of the ones we actually didn't talk about. So this is homework problem 7. Homework number 5, problem 7. It's actually very easy, but it's very easy to overthink and not set up correctly. So it simply says we have a 10-meter chain that weighs or has a mass of 80 kilograms. And we want to lift one end 6 meters off the ground. So the way you can kind of think about it is there's just this chain, piled up sitting on the floor. And then we're taking one end and we're just lifting it up to a height of 6 meters. So let me draw a little bit more basic picture. We have some chain sitting on the floor, and then we're lifting it up to a total height of 6 meters. So how do we find work in this case? So work, the integral of dw, is the infinitesimal amount of work done on some sort of infinitesimal amount of, or infinitesimal piece. And so we want to think of how we're cutting this up. And so you really want to think, if I cut up my chain into these tiny, tiny little segments, let's give it a variable. Let's say that it has a width of dy. And this y piece, or this single piece, is lifted to a height of y. So remember, this piece here started on the ground, and then I lifted that piece up to y. There's other pieces that got lifted up to a different height for a different y value. So in this case, for a given piece, it's going to have a certain amount of mass. So what is the force on it? On this guy, well, the force is constant. It has a fixed mass. And so there's going to be small amount of force on it, and I'm lifting it to a height of y. That distance is a fixed y in some sense. It's not a differential there. And what is this dF? Well, it's the amount of force that is pushing down on that tiny little piece. So tiny little piece, of course, there's a tiny amount of force going to be on it. And well, what is the force? It's just going to be the mass times gravity. But again, it's a tiny piece. So of course, gravity is a constant, and now it's just the infinitesimal piece of mass that piece of chain holds. So what is our dm? Well, the infinitesimal piece of mass is just going to be essentially the width. We're considering this chain as a one-dimensional object, so it's just a length of dy times the density. And what is density? The density we can obtain from the information given about the entire length of the chain. So remember, density is given as its mass per length, or mass, sometimes it's mass per area, mass per volume. Depends on how many dimensions our object is. So this is just a one-dimensional object, so it's going to be mass per length. and we consider it as uniform. So it's just going to be 80 kilograms per 10 meters. In other words, 8 kilograms per meter. So all in all, what do we have for this? We have the integral of the mass is now 8 dy. So we will have an 8, we will have a g, we have the y as the distance, and then the dy is the thickness of that piece of rope or piece of chain. And then all pieces of chain, I am lifting those to a y value range between 0 and 6 meters. So an easy integral. If you want to leave g as g, I honestly don't care. If you want to write it as 8g, that's fine. If you want to plug in the number 9.8, also fine. But again, I mean, you guys don't have calculators, so it's kind of like, do you want to multiply 9.8 times 8, or just leave it 9.8 as g? That's perfectly fine. And then, of course, you got an easy integral of y dy. Any questions on that guy? Okay, so let's do a trough one again. I think those ones are the trickiest between the trough ones and the hydrostatic pressure ones. So I want to do a trough one. Maybe we'll do another hydrostatic pressure one on Monday, just as a warm up. Because there it's like, it's easy to overthink and kind of get lost in the number of steps. Like I like to break things down like this, one piece at a time, to kind of organize my thought processes. So let's see, we've got a trough that has this kind of prism-like base. And then this one actually has a spout at the top. And the dimension, so it's 8 meters deep, 3 meters high, and 3 meters wide. The top, so this little spigot that comes out of it, is 2 meters high. It's filled with water up to the top, and we want to know how much work is done. Pumping the water out. So always be a little careful with these. You do want to mind where the water sits. So it's kind of a little hard to draw there, but we're going to assume that it's completely full of water. So the water is going all the way up to the top. Of course, it's not coming out the spigot or anything yet. We will have to pump that out. And so what do we want to do? Let's break it down and try to figure out how much work is done for each of these. So how are we going to break it up? So again, work is force times distance, but the force is the force of gravity. So any horizontal slice, since it's all at the same distance, or since it's all being moved the same distance out, it will be, it will require the same amount of work. What did I say? Did I say force was work, mass times gravity? Work was force times? Work is force times distance, and the force is constant with gravity. The only thing changing is distance. So a horizontal slice will all move the same distance vertically against that force. So we kind of cut it up into these horizontal cross sections. And the amount of work to move that whole thing out is going to depend only on that total mass of that, the total force on that, and the distance it is. the depth below. So let's kind of go through this thought process. Work is dW, which is going to be the amount of force on this slice. So since I'm cutting it up, it's going to have a small amount of force on it, and the distance we're moving it. So this is where we want to choose our reference point. So good reference points, we could always pick the bottom, not too bad. The top here, not a bad point. You could even try to pick the top of the spigot. Any suggestions? Any methods you guys want to see? Or you want me to just pick one? It should all work out the same. It's just that the numbers are going to be shifted around a little bit different. So let's pick the top of the water. Let's just pick right here as our origin. And let's define a variable. So this slice, of course, is going to have, it's going to be at a depth y. So let's measure y going downward. So the bigger the y values, increase downward. So it's like the opposite orientation of our standard coordinate frame. And the width of these guys is, of course, dy. So the work done in moving this slab out of it is the total force on it times the distance we're moving it. Well, I need to move it y to get up to my reference point, but then I also have to move it 2 more meters. So the full distance we're moving it is 2 plus y. So this is my force times the distance. And so now we have to just figure out, okay, what do I mean by this force that is on this infinitesimal slab? That is going to be, so you could do it as gravity times mass, or we could do it as gravity times density times the volume. So of course, density times volume just gives me mass. Gravity times mass gives me the force. And the dV is really what we should be thinking about, because each of these slices, of course, have some infinitesimal piece of volume. So dV is the volume of this guy. That's going to be the area of each slice times its thickness of dy. And the area is something we're going to have to figure out. So the area, I mean the top area, so its length times its sort of depth into the page. The height is just a dy. So let's draw our triangles. We got to use geometry in almost all of these problems. If you haven't sort of broken down the geometry of the tank anywhere, it's probably something you're missing. Work. So I know that the total trough has dimensions 3 by 3. And we want to know, in some sense, we just have to figure out the width of this slice. The depth, or the length, I guess we could call it, is always 8. That's one nice thing about the geometry of this trough. It's always got a length of 8. So that dimension we don't have to worry about. We've really got to find this guy here. And we measured that distance as y. So y was our distance from the top to the depth of the water, or to the depth of this slice, which means that this other side is going to be 3 minus y. We need to find that because that is the height now of this bottom triangle. So they are similar triangles, and you can see what is the ratio. So the width to the height, the ratio of the width to the height is always 1 to 1, which means this width has to be the same as this height. So this side has to be 3 minus y as well. And if you're not sure about that, you can always do it in a few steps. You can always introduce more variables. So for example, if you wanted to first say, I don't know what this side is, I need to find it, and I know it's, let's call it W. Then by similar triangles, you would just say, you could either do this width to this width, so our small width to the top width has to be the same ratio as the smaller height of my triangle to the full height of the triangle is one ratio you could set up, or you could set up an analogous ratio of the width to the big width. So this width to this width has to be the same ratio as this height to the full height. Of course, since both the dimensions are 3, those are literally exactly the same ratios. And then, of course, when you multiply the 3 over, you find that the width was 3 minus y. So now, what is my area? Area then is going to be 3 minus y. Width times the length was constant 8, and then it has a thickness of dy. And so we can plug this guy in now for that piece. And so our total work is going to be gravity times density. And then now our dV was 8 times 3 minus y. I'm going to put the 2 plus y, that is the distance we're moving each piece out, just so I can move the dy at the end there. And so our last bit are the bounds. And bounds, again, are another thing we got to think about. Just be mindful of your reference point and your orientation. So our reference point, our origin was right here. The bounds are always the where do my slices exist? So I'm starting here, downward is positive, so my slices exist from 0 all the way down to a depth of 3. So 0 to 3 for the bounds for that. And again, if you want, you can fill in these constants. Gravity was 9.8. We are using meters, so the density was 1,000 kilograms per cubic meter. Density is another one of those things that if you want to leave that just as rho, since it's a constant, not a big deal for me. If that comes up on your homework problems or something like that, you might have to fill it in for exams. But any sort of free response problems, I'm not a big stickler for filling in constants. A constant's a constant, and if it shows up at the end as a constant, I'm fully aware of what it means. The key things we want to see is, are you able to break down the geometry and come up with a correct expression for that, for the total work? Any questions? Anyone still writing? Okay. So our last problem we want to take a look at in these applications is a center of mass. We didn't get to do a problem yesterday on center of mass. And don't get too bogged down by the formulas. So we have center of mass. So find center of mass. They also call it the centroid of the semicircle. bounded by, so let's just give a generic radius. Y is equal to square root of r squared minus x squared. So we've got semicircle, y equals square root of r squared minus x squared. And we want to find the center of mass of this guy. So one thing we can always use is symmetry. So by the symmetry, the x center of mass is going to be 0. If we wanted to set that up, so just for posterity, I almost always like to do these center of mass problems, do them in pieces because there's a lot. It's just, these usually aren't too hard. There's just a lot of pieces to pick out most of the time. So what do we need? We need the moments and then the mass. So assuming uniform density, meaning that it's not weighted differently at any given point. It's all the same density at every given point. Then what is our mass? The mass is just going to be the density times the area. And area we know how to find. It is just going to be the integral of the lamina, the area under the curve. And if you want, you know how to do this now with a trig sub. Of course, we can also use known geometry in this case. So it will be just whatever the density is times area of a semicircle is going to be 1/2 pi r squared. So now remember, our x bar, this notation is going to look a little weird. It's the moment about the y-axis divided by the total mass. So just to set that up, if you forget the name of these guys or forget the correct variable label, don't worry about it too much. Just remember, what do we have to do? We have to take the mass, or every piece of mass, and just weight it by its x coordinate. So that's all that is. And of course, we need a row. So this is like the area of each piece. Weight each tiny little piece of area by its x coordinate. And since it's uniform density, to get mass, we would just pull out that row. And then, of course, we would divide that by our row over 2 times pi r squared. Of course, we already did x bar by symmetry. If you want to check that, compute this integral. That one now you can do by a fairly easy u sub, and you should find that this top integral should give me 0. The y coordinate, so we want to do similarly. We already found the mass. And let me start it on a new page since we'll actually have to compute this. The centroid y coordinate, of course, we call it the moment about the x-axis divided by the mass. And the moment about the x-axis, if you forget to change the labels, I know it's a little weird since it's y and x. Just remember, if we're finding the centroid for y, I want to weight the normal mass integral by a y. And actually, in this case, that's not going to work very well. And I'll explain this in a second. Let's finish writing it. So minus r to r. Sorry, I'm getting ahead. This is the Calc 3 way to do it. Really, we want to weight each thing by a y. But Calc 3, we would do this as a double integral, and we'd be able to essentially integrate and change the variables and integrate with respect to y. What is the formula we have, this sort of cheating formula that we came up with in Calc 2, is that really, since we are slicing things up vertically, what do I mean by y? This y coordinate is the center, the average y coordinate of each individual slice. So while we are weighting the function or weighting each piece of area by our y, really it's this y value, which is actually going to be here. Let's label it as our 1/2 f of x. So this is kind of our Calc 2 way of getting around having to do double integrals. And so we just get a 1/2 f of x squared, which will be r squared minus x squared. And then, of course, we have a density on the outside. So I forgot the density up here. And then the mass, of course, we found. Mass, I would say, almost always start with that integral. Kind of just how we did this. I started off finding the mass because that mass is going to come up in each of these x bar and y bar computations, and you don't want to have to keep writing extra integrals in there. It's easy enough just to find out whatever it is. So just to kind of write it in formulaically, what did we just do? This is our 1/2 f of x squared. This is the formula we came up with yesterday over the mass, and then times the density. And then now this guy is a pretty easy integral to do. Let's simplify the constants. So the rows will cancel. It looks like we will have a 2 divided by pi r squared times the integral of, sorry, that 1/2. That 1/2 will cancel that too. So we'll just have r squared minus x squared dx from minus r to r. And so what's that? So we'll get 1 over pi r squared. We need to integrate this guy. So we will have xr squared minus 1/3 x cubed from minus r to r. And then when we evaluate it, what happens? We've got 1 over pi r squared. And then we will have r cubed minus 1/3 r cubed minus, now when I put a negative here, that'll give me another r cubed, since I'll have a negative squared No, sorry, I'm plugging in for x. We'll have a negative r cubed there. So we only have one power of x. And then when I have a negative r cubed for that guy, it'll be negative. So that will be a plus 1/3 r cubed. And so all in all, what do we get? 1 over pi r squared. We've got r cubed plus r cubed, so it's 2r cubed minus 2/3 r cubed. And so what does that give me? 2 minus 2/3 is 4/3. So it's 6/3 minus 2, yeah. So 4/3. We'll have a pi in the denominator. We'll have r cubed in the numerator divided by r squared in the denominator. And so we should get something like this. 4 over 3 pi r. So check. Let's do some mental checks. Does this make sense? So our center of mass, xy coordinates, is 0, 4 over 3 pi times r. Is this a reasonable thing? We should check always. Did we end up with a point that is in the area that we actually contain? And did we? So of course 0 is here. 4 over 3 pi r, well, of course the top here should be at r. And of course pi is about 3.14, so this is about 4/9 or something to that effect, maybe a little smaller. So 4 out of 10, so it looks like the center of mass. So 3 times pi is going to be, I think that's going to be over 10, so it'll be like 4/10-ish, so somewhere less than half. So it looks like my y center of mass will be about there. So that seems reasonable. Any questions on that guy? Okay. Anyone still writing? Okay, so let's talk about sequences. So a sequence is an infinite ordered list of numbers. So you can think of it as just a specific order: 1, 3, 5, 7, 9. This is a sequence that describes the next each successive odd number. Or of course, there's things like the Fibonacci sequence, where the first two numbers are 1, and then every number after that, we just add the previous two numbers together. So to get the next term, I add 2 plus 1 to get 3. 3 plus 2 to get 5, 5 plus 3 to get 8, etc., etc. We can describe sequences with set notation. So I don't know how much you guys have seen set notation. It's usually just these squiggle brackets. Our set means anytime we have a squiggle bracket, it means we're just looking at a collection of numbers. And usually we need to describe those numbers in some way. So sometimes we can just list all the numbers. So A1, A2, A3, etc. Or sometimes we kind of shorthand it and we'll write something like AN, and N is 1, 2, infinity. So for example, if we write a sequence like this, what does this mean? So this, in some sense, you can kind of think of sequences as just functions. This is the same as writing, sometimes we'll write it as a closed form expression, n over n plus 1. Or if I want to list out all the numbers, so we usually start our n's at 1. Sometimes n will start at 0. Sometimes it'll start further down the road at 2 or 3 or something like that. If I plug in 1, what do we get? We get 1 over 2 is my first number. And then we pick the next successive integer. So the next value we pick is 2. When n is 2, we'll get 2 over 3. When n is 3, we'll get 3 over 4. And then that'll keep going. So let's add this note. We can think of sequences as functions whose independent variable is the natural numbers. So this is really all it is. I think it's kind of easy to almost overthink what's going on with sequences because it is a bit new notation and a bit new kind of ways to think about just ordered lists. Doesn't really seem very calculusy at the moment, but really it's kind of a different way of studying functions. So like if we kind of look at this previous example, when I write an equals n over n plus 1, we usually use n just to mean natural numbers, 1, 2, 3, 4, all the way up to infinity. This is essentially the same as looking at a function, f of x is x over x plus 1. Whereas here, my n is like my independent variable, natural numbers. Here, of course, it's my x's. But instead here, if we just thought of these x's as integers, 1, 2, 3, 4, 5, that's essentially what we get out of the sequence. And of course, likewise, when we're considering things like 1/2, 2/3, 3/4, these lists of numbers, well, how did I find these? This was A1. We plugged in 1 for n. This term was A2. We plugged in 2 for n. This term was A3. This is essentially the same as looking at the list of f of 1, f of 2, f of 3. So when we want to consider things about sequences, we often just want to consider things that we normally are thinking about in terms of functions. Let's see a couple more examples, though. So we can do sequences like square root of n minus 3, where n now starts at 3 to infinity. This is the same as writing a function as square root of n minus 3. And then, of course, now I have maybe a different domain. My domain of inputs starts at 3 and then goes up to infinity. So we often, next to writing our functions, sometimes we have to specify our domain, n greater or equal to 3. And then, of course, the list of numbers is 0. I plug in 4, we'll get 1. I plug in 5, we'll get square root of 2. 6, we'll get square root of 3. And this was, so A3, A4, A5, and A6. There are certain things, though, in sequences that don't come up as functions. So again, I can kind of think of this as analogous to the function f of x is square root of x minus 3 with x bigger or equal to 3 as my domain. Essentially the same thing, except here we kind of imply that we're only considering integer values, and here we can usually think of x as being fractions in any number that we want. The behavior of these guys, though, either out infinity and kind of the shape they take, is going to be very similar. So there are things in sequences so I'll say there are functions that come up, and actually in functions we could say, let's say operations. That come up in sequences that we haven't seen that we can't describe as a function. So sorry for being a little bit redundant there. As a function, what do I really mean? I mean kind of like mathematical operations or sort of mathematical computational notations that we can describe using the natural numbers when our natural numbers is our domain, that we usually don't come up with in sort of our traditional function sense in calculus. Like we don't have, in calculus, we've studied all continuous functions. When now I change my function to a domain of natural numbers, it doesn't quite have an analog to extending it to a continuous function on all of the real numbers. So what do I mean by that? Let's see. So the first thing that comes up is this alternating series. So I could write something like -1 to the n over, let's say, 2 to the n. And I'll say starting at 0 to infinity. The analogous sort of closed form expression of this is -1 to the n over 2 to the n. And if we were to write out some numbers, what do we get? So when n is 0, I get 1 over 1, that's just 1. When n is 1, what do we get? Well, that'll be a -1 in the numerator. The denominator will be 2. That's my A1 term. And then my a2 term, now my numerator, negative 1 squared, goes back to a positive. And the denominator, 2 squared, gives me 4. And so you can see what's going to happen. Each of the odd terms are going to have a negative 1 raised to an odd power. So those will be a negative value. Whereas each of the even terms are going to be raised to negative 1 to an even power. And so those will be positive. So this doesn't quite have an analog. You might kind of think of this as something like, I mean, the closest analog we can get to something like a minus 1 to the n might be something like a sine or a cosine, right? Because sine and cosine oscillate between plus and minus 1. The problem is they take a lot of values in between, right? There's not, so let's write this out. So minus 1 to the n doesn't quite have an analog. As a continuous function. So if I have an, if we just pick out this alternating series, and again, if we consider n starting at 0 or 1, what's this series going to do? Well, this is just going to be, let's say n starts at, let's keep starting at 0 in this case. So it'll just be 1. When n is 1, it'll be negative 1. When n is 2, it'll be positive 1, and then negative 1. This doesn't quite work as a function, because what is f of x equal to minus 1 to the x? We never see this. This has never come up before. And why not? Specifically, right, what if x equals 1/2? Right, then we have negative 1 to the 1/2, which is square root of negative 1, which we don't like. We can't do. Or even more crazy, what if x is pi? What is negative 1 to the pi? We can't quite do. So we're taking all this knowledge that we had of functions, but now, sort of interestingly enough, when I change my domain just to natural numbers, we get some extra operations. And so we kind of have to learn now how to deal with these extra operations and how we can use them to describe new sequences, and moreover, what are their effects. So the other one I want to talk about that will often come up is factorial. This is another one that we often see in, it's like a new operation, a new function, so to speak, that we can't write as a traditional function on the real numbers. Or at least the way we would do that is beyond the scope of this course. So our factorial notation, we will often write like this. It's an exclamation point. So n factorial is how we read that. What does this mean? This means whatever number I start with, I'm just going to take that number and then multiply by all of the integers less than that number and including that number. So for example, if I have 3 factorial, what does that mean? That means 3 times 2 times 1. which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. Let's come up with a sequence. I could say an is equal to, let's throw in a little bit of everything. Let's say minus 1 to the n. Let's say 2 to the n divided by n factorial. And actually, let's change this a little bit. I'm going to say minus n plus 1 because I want my n to start at 1. So if it's not specified, let's just assume n starts at 1. So I specified it there again, still starting at 1. So what are the first few terms of this sequence? So let's plug it in. When I plug in 1, we will have minus 1. N plus 1 will give me a 2 times 2 to the 1 over 1 factorial. So what is that? That's just going to give me a 2. 1 factorial is just 1. So that'll just give me 2 for that first term. So this is my A1. My second term, A2, we're just plugging in 2 for n. So we will have minus 1. 2 plus 1 gives me a 3 times 2 squared over 2 factorial. So that'll give me a negative there. We'll have 4 in the numerator, divided by 2. 2 factorial is 2 times 1. And so we will just get 2 for that second term. Let's list out a few more. So we don't have space there. Let me just write it out as a list. So let's say A3 is then going to be equal to minus 1 to the 3 plus 1 is 4, 2 cubed over 3 factorial. Positive 2 cubed is 8. 3 factorial is 3 times 2 times 1. So we will have 8 divided by 6 now, or 4/3. And let's do one more. Let's find A4. We'll have minus 1 to the 5, 2 to the 4th over 4 factorial. So again, that one will be negative. 2 to the 4th is 16 over 24. So we found 4 factorial. 4 times 3 times 2 times 1, 24. How's that simplify? So divide by 8, looks like we get 2/3 when we factor that out. Does that make sense of how to compute these factorials? We'll keep playing with this because it is new and it'll show up on some of these WebAssign. So one thing to note though is look at what's happening. We have an exponential function in the numerator, 2 to the n. Exponential functions grow really, really big, really, really fast. The denominator is this factorial function, n factorial. And let's look at the terms. So you can kind of see the first term was 2. The second term also ended up being 2. But then what's happening? The third term is 4/3, so still bigger than 1. But what about the fourth term? Now less than 1. And you can see that these factorials, even though 2 to the 4th is starting to get pretty big. What's the next one going to be? It's going to be 2 to the 5th. Did I miss my minus sign? I did. Negative there. I forgot my alternating, and it looks like I missed the minus sign here too. So that guy should have been negative. But in absolute value, the overall size of the numbers is getting smaller and smaller. So these factorial functions actually get really big, really, really fast. Factorials grow faster then exponentials. So they get really, really big, really, really fast. So if I just wanted to write that, so no matter what base of b I choose, as long as b is bigger than 1, even if I choose a base 10, 10 to the n, it's going to get really big. 10, 100, 1,000, 10 to the fourth is 10,000. It's still going to be smaller than n factorial as n grows. So for large enough n's, these guys are going to start off bigger, but eventually as n keeps going, these guys are going to surpass them. They're going to go to infinity much quicker. And I think we'll see that a little bit more coming up, and we'll play around with these, the algebra of how to play around with those, finding limits, and how to simplify those when they come up with sequences and in ratios and whatnot. Can be a little tricky to see at first. And we'll talk about those more next week. For now, I just kind of want you to get the idea that how to compute them. It's just multiplying consecutive terms. And then just an idea of why that they grow really fast, just based on this example. And maybe we'll try to prove that a little more rigorously in the next few days. Let's do some practice now, though, of just coming up with some closed form expressions of sequences. And then maybe introduce this notation of a limit. So we have an example. So find a formula for an when we're given the sequence 3/5 minus 4 out of 25, 5 out of 125, negative 6 out of 625, and then 7 over 3125. So it is common practice. If I'm given a list of numbers, we want to actually find a formula that will match it. You can kind of think of this as given a table of values. Sometimes, like we've done a lot of this with Riemann sums. We can consider the n values. The n value that we start at is actually kind of arbitrary. We can always pick whichever one we want. But since it's not given, let's just assume that this guy corresponds to n equals 1, n equals 2, n equals 3. So in some sense, you can kind of think of this as these tables that we see. Where we've seen a lot of tables of functions where I give the x value in the top, except now instead of x, we have n. And then in the bottom is my function, f of x, and now listed as a sub n. And let's see, n equals 5 was the last guy, 4, 5. So we got 7 over 31, 25. And of course, we've done a lot of work with tables, doing Riemann sums. Sometimes we find slopes between these and approximate derivatives. Now we actually kind of want to find a function that fits this the best. If I want to find a function that will match these values, this case we can actually do it. Of course, in Calc 1 and Calc 2 for continuous functions, well, we may not know the function could do crazy stuff in between each of these numbers. It might not just go from this number to this number very nicely. It could have humps and valleys. In this case, though, since we are dealing with only integer values, we can find an explicit closed form expression for this sequence, or at least we can attempt to. I will give you guys a warning that sometimes we cannot do this. If we need to find a closed form expression for an, it's always good to try. There are certain sequences that sometimes we just cannot come up with a nice expression for a function that will bounce around these guys. Okay, so let's try to think of what's happening. Usually when you're given a rational expression, let's try to break it down into both numerator and denominator. So what's the sequence in the numerator? Let's actually attach the negative signs to the numerator as well. So the numerator is going to look like 3, -4, 5, -6, 7. That's not too bad, right? If it's alternating, so anytime we have this plus minus thing going on, this -1 to the power of n, we call that an alternating sequence. So if it's alternating sign, plus minus, ignore that for a second. Let's just look at what are the actual numbers doing. 3, 4, 5, 6, 7. It's pretty easy. It's just increasing by 1 every single time. So you can think of it as a linear function. And what is the slope? If I increase my integer by 1, the value, so think of these guys, right? My function values are like my y values. So the change in the y value is just 1 with a 1 change in the x. So the slope is 1, but my starting value is 3 when n equals 1. So this is my an. So we can use point slope form, right? Think of these guys as my x values, these guys as my y values. And of course, this is just picking out the sequence of the numerator now with ignoring the alternating. So how do we come up with a sequence of 3, 4, 5, 6, 7 when I start at 1? Well, it's just going to be, think of it like this. Y minus 3 is equal to my slope, x minus 1. Point slope form. I had 1, 3, and my slope. And then now what is my y? Think of that as like my an. And actually, let's use a different letter. Let's call it, and actually, you know what? Let's call it y sub n. So of course, my a sub n is my general term. I want to use different letters because I'm picking out what we might call subsequences or sequences that are relating to the pieces of the sequence for the general sequence. So what is that going to be when I distribute? It's just going to be, I replace the x's with n, and we'll just get n plus 2. So really what's going on in my numerator I have an alternating sequence, so we're going to have a -1 to the n, and we'll take a look back at that in just a second, and then I'll have to have times this n plus 2. And now let's check. Let's always come back to this alternating just to check to see if it starts at the correct value. So this was my general term for the numerators, and we can check if I plug in 1, we'll get 3. If I plug in 2, we'll get 4. 3, we'll get 5. So the index is correct with that of where we're starting with this plus 2. However, let's check the minus sign, make sure that is correct. If I plug in 1, what's my first sign? It'll be -1 to the 1. It'll give me a -3. If I plug in a 2, we will have a -1 squared which will give me a positive 4. So my minus signs are off. How do we correct it? So the minus signs are easy. If there is an alternating, it's always going to be a -1 to the n, or you can shift it by a +1. You can either do a +1 or a -1 in the exponent for your -1 to the n or -1 to the n plus 1 to just shift all the signs. This is what we saw in one of the previous examples. So check it again. So when n is equal to 1 now, the numerator, excuse me, the exponent here will give me a 2. So it'll be -1 squared, and then n is equal to 1, we will have that positive 3. When n is equal to 2, we will have -1 cubed, which will give me that negative, and then my 2 times plus 2 will give me that 4, so -4. So this is my numerator sequence. Denominator, let's take a look at what's going on. Denominator goes 5, 25, 125, 625, 3125. So what's going on with this guy? What type of function describes this? Hopefully you guys can see, well, how do I get between the first two numbers? Some things you want to check. So here, of course, if I ignored the alternating, we just saw 3, 4, 5. That's just add 1, add 1, add 1, add 1, which gives me that slope of 1. So sometimes it's a linear function if I'm just adding a constant value. Of course, what's going on here? I'm not adding a constant value. We are continually multiplying by a constant value. So 5 times 5 gives me 25. Times 5 gives me 125. Times 5 give me 625. So we have this constant multiplicative factor of times 5. So what does that mean? If I am constantly multiplying by 5, we are going to need an exponential function. So let's think of it, let's use now say z as our dependent variable. So think of our function as z is equal to a b to the x. But our b is our multiplicative factor. So it should be something like 5 to the x. And now we just need to figure out the starting value. So of course in sequences, this is z sub n for our denominator is equal to some constant a times 5 to the n. There's no extra alternating or anything going on. So now we just have to figure out, well, if I'm starting at n bigger or equal to 1, do I need an a value? So of course, if I plug in 1 to n, we will have 5. If I plug in 2 to n, we will have 5 squared. That'll give me 25. If I plug in n cubed, it'll give me 125. So you can check values. I know that, so z sub 1 is equal to 5 is equal to a times 5 to the 1. So this value I got from the actual sequence. Likewise, you can check other points, just like you would for functions. Pick different values of x. If we're given information about a function, essentially a function will pass through certain points with an x value of 1, y value of 5, x value of 2, y value of 25. You can use those points to solve for sort of maybe extraneous or extra variables that might appear in that function. In this case, it's pretty easy. Our z2 was 25. which we're modeling by a times 5 squared. And of course, from each of these equations, either one we pick, if we try to solve for a, what do we get? A is equal to 1. So this one's not too bad. Of course, refresh exponential functions, if you're a little unfamiliar with this, right? It could be the multiplicative factor could always be 5, where I'm multiplying by 5 every time, but sometimes the starting value might be 2. So it could be like 2, 10, 50, 250, where I'm multiplying by 5 every time, but because the starting value, this a value, wasn't a 5 or a multiple of 5, the sequence could look different. Okay, so our a was 5, and so what is our denominator then? Our z sub n we found is just 5 to the n. Nothing too fancy, basic exponential there. So all in all, how do I find the general expression? It's just going to be the numerator divided by the denominator. So our a sub n was -1. We had an n plus 1 times our n plus 2 divided by the denominator was just 5 to the n. And again, check that. If I plug in 1, we will get a 3 times a positive number. And of course, in the denominator, we'll have 5. If we'll plug in a 2, we will have a 4 times -1 cubed gives me a -4 over 5 squared gives me 25. So we check a few values and we see that that's a good expression for our sequence. All right, any questions on these guys? Cool, so it looks like we only got 0 minutes. Class time just ended. So go ahead and stop there. Have a good weekend, and then I'll see you guys on Monday.
Bye, thank you.